Imagine a medical scan where a tiny tumor hides in plain sight, so subtle that even an expert might miss it. Now imagine a model that learns what normal looks like from thousands of healthy scans, and then spots deviations with near-perfect precision, without ever seeing a single abnormal image during training. This is the promise of unsupervised anomaly detection, UAD, a critical task in medical imaging, industrial inspection, and beyond. But while the idea is elegant, the reality is messy. Most state-of-the-art methods rely on storing vast numbers of feature vectors in memory banks, performing expensive nearest neighbor searches at test time, and sacrificing speed and scalability for accuracy. In this video, we dive deep into a new approach that flips the script: spatial autoregressive modeling of DINOV3 embeddings, a framework that achieves top-tier anomaly detection performance with minimal memory, single-pass inference, and no need for bulky memory banks. Let's unpack how it works. Hash the problem: ignoring spatial structure. Modern vision models like DINOV3 extract rich, patch-level embeddings. Each patch of an image becomes a high-dimensional vector encoding both semantic meaning and spatial context. These embeddings are already globally contextualized through self-attention, so they know what a region is and where it sits in the image. But here's the catch: most current UAD methods treat these embeddings as independent data points. They extract patches from normal images, model their marginal distributions, often using memory banks or clustering, then compute anomaly scores based on how far each patch is from the learned normative distribution. This ignores something crucial: the spatial relationships between patches. Even if a single patch looks normal, a cluster of them forming an abnormal shape, say, a lesion in a brain MRI or a crack in a steel surface, can be a red flag. Yet, treating patches independently means the model loses track of this structural integrity. Moreover, memory banks require storing tens of thousands of embeddings, and inference involves comparing every test patch against all stored ones, leading to slow runtime and high memory usage. This is a major bottleneck in real-world clinical deployment, where speed and efficiency are non-negotiable. Hash the solution: a 2D autoregressive model. Our solution: model the joint spatial distribution of DINOV3 embeddings using a 2D autoregressive AR framework, a simple yet powerful idea. Instead of treating patches as independent, we model the full embedding grid as a sequence of predictions, one patch at a time, conditioned on all previously processed patches under a raster scan ordering, top left to bottom right. Mathematically, this means PF equals \prod ij P, Fij \mid Fij, where Fij is the embedding at position ij, and Fij denotes all embeddings that come before it in the scan order. Each conditional distribution is modeled as a simple isotropic Gaussian. PFij \mid Fij equals \mathcolon Fij \mid /mui j I. The mean \mui j dollar is predicted by a neural network that only sees the past context, enforcing the autoregressive constraint. The model is trained by minimizing the negative log likelihood. \mathcolel \theta equals \frac1x \texttrain \sum x in x \texttrain \sum ij log p Fij mid Fij \theta. At test time, the anomaly score for each patch is simply the negative log likelihood of its prediction. Aij equals \log p Fij mid Fij. And here's the magic: this entire process runs in a single forward pass. No iterative computation. No memory bank lookups. Just one pass through the network. # architectural innovation, masked convolutional AR. So how do we make this efficient? We use masked convolutions, a technique inspired by Pixel CNN but adapted for 2D embedding grids. Imagine a convolutional kernel operating on the embedding grid. To enforce autoregression, we set weights to 0 for any spatial location that comes after the current patch in the scan order, i.e., below the current row or to the right in the same row. In the first layer, we also mask the center pixel, so the network cannot peek at the current patch itself. In subsequent layers, the center is unmasked because intermediate features no longer contain raw input data. This allows us to parallelize training and inference, no sequential evaluation required. The model learns to predict each patch based on its spatial neighbors, but in a way that respects the causal order. But here's a deeper insight: DINO embeddings are already highly contextualized. Neighboring patches often look nearly identical due to smooth anatomical structures. A naive CNN might learn to just interpolate locally, predicting a patch based only on its immediate neighbors. This is dangerous. If a region is structurally abnormal but still surrounded by normal patches, the model might still predict it correctly, leading to missed anomalies. To combat this, we introduce dilated convolutions, a simple architectural tweak that expands the receptive field without adding parameters. By inserting gaps between kernel elements, we enable the network to capture long-range spatial dependencies, the kind of context that helps distinguish real anomalies from plausible local interpolations. This gives us a flexible trade-off: a standard AR model for local, high-resolution prediction, and a dilated AR model for broader context. # experimental results: speed meets accuracy. We evaluated our method on the BMAD benchmark, a comprehensive medical anomaly detection dataset including brain MRI, BRA-TS 2021, liver CT, BTCV plus LI-TS, and retinal OCT, RESC. Let's break down the results. On BRA-TS 2021, our dilated AR model achieves 98.35% AUROC, nearly matching AnomalyDINO v3's 98.38%, while running over 10x faster and using significantly less memory. More impressively, on AUPR, a metric that matters more in imbalanced settings, our method leads all others with 72.42%, surpassing even AnomalyDINO v3's 69.49%. On BTCV plus LiTS, our standard AR model achieves the highest AUROC, 97.32%, outperforming AnomalyDINO v2's 97.24%, despite being far more efficient. On RESC, while PatchCore leads in AUROC, our method ranks second among dyno-based approaches with 56.16% AUPR, and crucially, with only 0.2 seconds per image. Now look at the runtime versus performance trade-off. Our method consistently sits in the upper left quadrant, high accuracy, low latency. Even compared to methods using DINOV2, our approach wins on both speed and efficiency. And the memory savings. Our model uses less than 1 GB of GPU memory during inference, versus over 8 GB for AnomalyDINO and over 20 GB for PatchCore. Ablation study, why it works. We ran several ablations to understand what drives performance. First, we tested a bidirectional AR model, where each patch is predicted using both past and future context. But this offered little improvement, suggesting that future patches don't add meaningful information. In fact, it sometimes hurt performance. Then we tried modeling anomalies directly in image space, a naive approach that fails completely. This shows that the embedding space is essential. The spatial structure must be preserved in feature space. We also tested scaling up the backbone from DINOV3's to DINOV3-7B. While AUROC dropped only slightly, 98.35 right arrow 98.25, inference time more than doubled. This tells us scaling the backbone alone doesn't help much in our framework. The power comes from the modeling strategy, not just the feature extractor. Conclusion: simplicity, speed, and sensitivity. This work demonstrates that explicitly modeling spatial dependencies in DINOV3 embeddings is not just beneficial, it's transformative. By replacing memory banks and nearest neighbor searches with a lightweight parametric AR-CNN, we achieve competitive detection performance across multiple modalities. Single forward pass inference, no iterative computation. Minimal memory footprint, ideal for clinical deployment. Scalability, no need to store thousands of feature vectors. The key insight: the spatial structure of embeddings is not just noise, it's anatomy. And by modeling it with a simple, masked, dilated convolutional network, we unlock both sensitivity and efficiency. This is not just a faster method, it's a smarter one. Final thought. In the race to build better anomaly detectors, we've often chased bigger models, more complex architectures, and richer representations. But sometimes, the most powerful idea is to think differently about the data itself. Instead of asking, how can I store more features, we asked, how can I model the relationships between them? And the answer: a 2D autoregressive model, simple, elegant, and surprisingly effective. If you're working on unsupervised anomaly detection, whether in medicine, manufacturing, or beyond, this framework is worth your attention. Because in the end, the best models aren't always the most complex. Sometimes they're the ones that understand the structure of the world, patch by patch, context by context.